We are going to start now the first chapter of class 12th mathematics, relations and functions, and this is our first lecture. So in this chapter we will talk about various types of relations. For basic definitions related to the relations, you can refer to our previous video of class 11th. The first definition we have over here, it is the reflexive relation. So we are saying, suppose we have a non-empty set A, and we know that a relation R on A, it is basically we are saying A is any set, we are taking the Cartesian product of A, and R is any subset of this A cross A, the Cartesian product, then R is called the relation on A. So a relation R, this relation we are talking about, is said to be reflexive if A comma A means when we are writing A is a subset of A comma A, we can write this as, if we are considering an element A comma B belongs to R, we can also write it as that A is related to B. So we are saying the relation R is reflexive if A is related to A for every A belongs to A. If we take any element from the set A, then that element is related to itself. That is, we are saying that each of the pair A comma A, it belongs to the set R. This definition will be more clear to you with our next examples. The second definition we have, it is the symmetric relation. So we are saying a relation R is said to be symmetric if A is related to B. We are taking any two elements A comma B that belong to A. We have chosen two elements A and B from A, and if A is related to B, then we are saying this thing implies that B is related to A. And if this thing holds for all A comma B belongs to A, then we say that the relation is symmetric. The third definition we have, it is the transitive relation. So a relation is said to be transitive if A is related to B and B is related to C. This thing implies us that A is related to C. These are just the definitions I am telling to you. These definitions will be more clear to you with the examples that we are going to do after these definitions. And a relation is said to be, the last definition on this slide we have, it is equivalence relation. We are saying a relation is said to be equivalence relation if it is reflexive, symmetric and transitive. That is, it satisfies all these three properties, then it is said to be equivalence relation. Now we come to our first example. So it is, let A be the set of all triangles. A is any set and it is set of all triangles in a plane, and R is a relation defined by two triangles are related if they are congruent to each other. For congruence, definition of congruence, you can refer to our videos of class 9th where we have studied the congruence of the triangles. So we have to prove that this relation is an equivalence relation. So the definition of equivalence relation we have is, we have to prove three things. First is, we have to prove that this relation is reflexive. Second, we have to prove that this relation is symmetric. And third, we have to prove that this relation is transitive. The definition of reflexive we have is, we are saying any set, if any set A is given, we have considered that, we are saying that for all A belongs to A, this thing implies that A comma A belongs to the relation R. Now in this case, in place of this A, we are having, not in place of, the definition of this A we have, it is A is the all triangles in a plane. It means this element A we are talking about, it is from this set A, so it is a triangle in the plane. We are talking about this thing, A belongs to A means we are talking about we have chosen a triangle from the plane, and the relation R is that if we have chosen two triangles, then they are related to each other, that is they are congruent to each other. And suppose we have chosen a triangle delta, we have shown this thing over here, we are saying that delta be a triangle that we have chosen from all the triangles, and we know that any triangle that is equivalent to or congruent to, we are saying itself, we are saying delta is related to A. What this thing means over here, that delta is congruent to A. What is delta? Delta is any triangle that we have considered. So we are saying any triangle that we have considered, it is related to itself by the equivalence relation, which is defined as the congruence of the triangles. That is, every triangle is congruent to itself. So this thing means that delta comma delta, it belongs to R for all values of delta in A. So this thing proves that this relation is reflexive. Next is, we are talking about the symmetric. The definition for the symmetric we have chosen two elements A comma B from R, and we are saying this is for all A comma B belongs to A. We have chosen two elements A comma B from A. We are saying if these two elements A is related to B, what this thing means over here, according to this definition of R, this thing means that A is congruent to B. If A and B, these are triangles, we are saying A is congruent to B, and this thing implies us that B is congruent to A, and B is congruent to A means that B comma A, this belongs to R. And this is what we have to prove. We are saying that if delta 1 and delta 2, they are from A, what is this thing, how you can read this thing? We are saying that delta 1 delta 2 are two triangles. Next thing we have is delta 1 comma delta 2, this belongs to R. What this thing means, that delta 1 is congruent to delta 2. We are saying if delta 1 is congruent to delta 2, it means delta 2 is also congruent to delta 1, and this thing means that delta 2 comma delta 1, it belongs to R. So we are saying this relation is also symmetric. Next definition we have, it is transitive. So for transitive, we are saying we have chosen the elements A, B, C from the set A. That is, we have chosen three triangles now. What we have to prove, that if A is related to B and B is related to C, in this case we are saying delta 1 is congruent to delta 2 and delta 2 is congruent to delta 3, then we have to prove that A is related to C. And we know that if a triangle delta 1 is congruent to delta 2 and a triangle delta 2 is congruent to delta 3, then delta 1 will be congruent to delta 3. This thing we have already proved in our previous classes, that if two triangles delta 1 delta 2, they are congruent, delta 2 and delta 3 are congruent, and delta 1 and delta 3, these are also congruent to each other. So this thing is shown over here. We are saying delta 1 comma delta 2 belongs to R. It means delta 1 is congruent to delta 2. Delta 2 comma delta 3 belongs to R means delta 2 is congruent to delta 3. Then this thing implies us that delta 1 is congruent to delta 3. And this is what we have to prove. Next we have is, let A be the set of all lines in xy plane. We are talking about, suppose this is the xy plane, this is x-axis, this is y-axis, and we are talking about all the lines in the xy plane. Now the relation R, it is defined in A, and it is defined like that L1 and L2, this pair we are talking about, this belongs to R if L1 is parallel to L2. So if we are talking about, suppose we have considered this is the line L1, then all the lines in the plane which are parallel to this line, these are related to each other. If we are considering, suppose these lines we are talking about, then all these parallel lines, these are related to each other. We have to prove that R is an equivalence relation in A. So the first thing we are talking about, it is the reflexivity. So for reflexive, what we have to prove, the definition of reflexive is that for all A belongs to A, we have to prove that A comma A belongs to R. That is, every element is related to itself. Every element is related to itself means, if we are talking about in this connection, we are talking about we have every line is parallel to itself. So we are saying that if L belongs to A, L belongs to A means we are talking about any line in plane. Then L is parallel to L means that every line is parallel to itself. It means L comma L, it belongs to R for all L belongs to A. Second we are talking about, it is the symmetry. So symmetry means let L1, L2 belongs to A. We are having two lines now. We are considering any two lines L1 and L2. Now look at this condition very carefully. We are talking about, we have considered any two lines L1 and L2, and they are satisfying this condition that L1 comma L2 belongs to R. That is, L1 is parallel to L2. We are talking about the collection of all those lines which are related to or we are saying we are considering all those lines L1 and L2 which are parallel to each other. Then this thing implies us that L2 is parallel to L1, and this thing implies us that L2 comma L1 is related to or it belongs to R. That is, L2 and L1, they are also related. Why I am saying that this condition is important, or how we are going to look at this condition? We are not saying over here that we are considering any two lines L1 L2. We are talking about particularly those two lines L1 and L2 which are related to each other. We are saying if L1 is related to L2, then we have to prove that L2 is related to L1. So this is our second part, that we are saying it is the symmetry. For symmetry, we have proved that L1 comma L2 belongs to R implies L2 comma L1 belongs to R. And the third thing we have to prove is transitivity. So for transitivity, we have considered three lines L1, L2, L3 which belong to A. It is given that L1 comma L2 belongs to R. It means L1 is parallel to L2. This is given that L2 is parallel to L3. Then it is clear we are talking about a plane. We are talking over here about a plane. So we are saying if L1 is parallel to L2 and L2 is parallel to L3, then L1 is parallel to L3. This thing will be true. So we are saying this relation is an equivalence relation. That is, it is satisfying all the three properties. That is, it is reflexive, symmetric and transitive. It is important to note over here that we are talking about A is the set of all lines in XY plane. We are not talking about the three-dimensional plane. The conditions might be different over there. We will see in our next chapters. Now the next thing we have to find over here, it is the set of all lines related to the line y is equal to 3x plus 5. So what this thing means is, we are talking about, this is the line given to us. Suppose this is this line we are talking about. We have to find all the lines which are parallel to this line, and we know that the lines parallel to the line y is equal to 3x plus 5, there y is equal to 3x plus k, where k is any real number. So what we obtain is that the family of lines parallel to the line y is equal to 3x plus 5, that are all the lines which are related to the line y is equal to 3x plus 5. Next we have is, let z be the set of all integers and r be a relation in z, and the relation r is defined like r is equal to a b such that a minus b is even. So we have to prove that this is an equivalence relation. So the first thing we have to prove is that it is reflexive. So we have chosen an element a from z. So we are saying a from z means a is an integer, we are saying. So we have to check whether a comma a, we have to check whether a comma a is a subset of r or not. It means we are talking about whether a is related to a, and how we check this is, we are calculating a minus a is equal to 0, which is even. It means this thing implies us that a is related to a. We have to check this thing, that a is related to a or not. So to check this, we have substituted this value, we have calculated this value a minus a, the answer comes out to be 0. We are saying it is an even number, it means every a is related to itself. Second thing we have to prove is the symmetry. For symmetry we are saying that suppose a comma b, these are two elements or two integers we are talking about, and what we have is that a minus b belongs to z. A minus b belongs to z means that a minus b is even. If a minus b is even, then b minus a is also even, and this thing implies us that b comma a, it belongs to r. We are saying this thing we have obtained from a comma b belongs to r, and this thing implies us that b comma a belongs to r, and this is true for every two integers. If we consider any two integers we are talking about, so we are saying that a comma b belongs to r, it implies us b comma a belongs to r. So this relation is symmetric relation. Next is for transitivity. We have considered three integers a, b, c, and they are such that a comma b is related, the a comma b, these are related elements, that is they belongs to r. B comma c, they belongs to r. These two conditions are given to us. It means a minus b is an even integer. A minus b is even integer means there is some number m for which this is equal to 2m, and b minus c is, there is some number n for which b minus c is equal to 2 times n. What we have to do is we have to check whether a is related to c or not. So we are calculating the value of a minus c. So if we subtract these or add these two equations, we will get it is a minus b plus b minus c, that is equal to 2 times m plus n. This b and b gets cancelled, so we get the value of a minus c is equal to 2 times m plus n. This 2 is there. It means a minus c is also an even number. This a minus c is an even number. It means a is related to c. So what we have is, for a comma b belongs to r and b comma c belongs to r, we have a comma c belongs to r. Next we have is, let a be the set of all lines in a plane and r be the relation defined by L1 is related to L2. We are talking about two lines L1 and L2 when L1 is perpendicular to L2. So first thing we have over here, it is, we are talking about the reflexivity, and we know that any line, it is parallel to L1 is always parallel to L1. If we consider any line L1, that from the set we are talking about, the set of all lines in a plane, we know that L1 is always parallel to L1. So it means L1 is not related to L1 by this relation. So we are saying that this relation R is not reflexive. That is, the element of the set A, they are not related to themselves. Next, second thing we have is that L1 and L2, suppose these are two elements we have considered from this L1 comma L2, these are the two elements from A, such that L1 is related to L2. This thing implies us that L1 is perpendicular to L2. This thing implies us line 2 will be perpendicular to line 1, and this thing implies us that L2 comma L1, they are related to each other, and this thing proves that this relation is symmetric. That is, if L1 is perpendicular to L2, then L2 is perpendicular to L1. Third is, if L1, L2, L3, these are three lines such that L1 is perpendicular to L2 and L2 is perpendicular to L3. We are talking about there is a line, say this is the line L2, and we have considered that there is another line in the plane L1 which is perpendicular to this. There is another line over here L3 which is perpendicular to L2. We are saying L1 and L2 are perpendicular, L2 and L3 are perpendicular. Then L1 and L3, they need not be perpendicular to each other. It means L1 comma L3, they are not related to each other, whereas L1 comma L2, they are related. L2 comma L3, they are related, but L1 comma L3, these two are not related to each other. So we get that this relation is not a transitive relation. Next we have is, let S be the set of all real numbers and R be the relation on S defined by R is equal to AB, 1 plus AB is greater than 0. So it means any two elements A and B, they are related if they are satisfying this condition. We have to prove that this relation is symmetric and reflexive but not transitive. So for first of all, we are looking at this condition reflexive over here. So definition of reflexive we have to choose any element A from S. We are saying for all A belongs to S, we have to prove that A is related to A. It means it satisfies this condition. So if we look at this condition over here, it will become 1 plus A into A. We are talking about this value, and this is equal to 1 plus A square, and this is always greater than 0 because we are saying A square is greater than equal to 0. So 1 plus A square is always greater than 0 for all A belongs to set of real numbers. Set of real numbers over here, they are represented with S because R we are using, the symbol R we are using for the relation. So what we get is that for all A belongs to S, we have 1 plus A into A is greater than 0. It means A is related to A for all A belongs to S. We have used this condition over here. So it means this relation is reflexive. Next we have is to prove it is symmetric. So suppose we are considering two elements A comma B from the set S, and we are considering these two elements, these are such that A is related to B. A is related to B means 1 plus A into B is greater than 0. So this thing implies us for real numbers 1 plus B into A is greater than 0. The multiplication is commutative, and this thing implies us that B is related to A. So it means for all A, B belongs to S such that A is related to B. This thing implies us B is related to A. It means the relation R is symmetric. Next we have to disprove that this is transitive. So to disprove, it is sufficient to give a counter example. To prove something, we have to give the proof, but to disprove this result that it is transitive, we are disproving this thing. So we are giving an example over here. Giving an example means we have to find the numbers A, B and C, and we have to prove that if A is related to B and B is related to C, then it is not necessary that A is related to C. As in the previous case, we have given the examples of the lines. Over here, we have to find the numbers. So suppose we are saying the number A we have that is equal to -1, B is equal to 0 and C is equal to 2. Then what we have is A is related to B. Why? We are saying 1 plus -1 into 0. This is greater than 0. This thing implies us A is related to B. When we are talking about B and C, we are saying 1 plus 0 into 2, that is equal to 1 and it is greater than 0. It means B is related to C. Now next thing we are talking about 1 plus -1 into 2. We are talking about this. A is 1, C is 2. So we have considered 1 plus -1 into 2. This is equal to 1 minus 2, that is equal to -1, and this is not greater than 0. This value, this is not greater than 0. So we are saying that A is not related to C. I think is not related to C. So what we have is for A comma B belongs to R, B comma C belongs to R, we have obtained that A comma C is not belonging to R for these real numbers. It means we have found a real number. There may be other real number also, there may not be, but one counter example is sufficient. We are saying that this property is not holding for all real A, B, C. It should hold for all real, but we have found that there are real numbers for which this property is not true. So we are saying that this relation is not transitive. Next is let S be the set of all real numbers and R be a relation on S defined by R is equal to A and B are related if A is less than equal to B. We have to prove that R is reflexive, transitive, but not symmetric. So again, for the reflexive part, we have considered the element A belongs to S. We are saying for all A belongs to S, A is always less than equal to A. So this thing implies us that A is related to A. So for all A belongs to S, A is related to A. It means the relation it is reflexive. Second, we are saying we are considering A comma B comma C. We are talking about now the transitivity. We are saying A, B, C are there such that A is related to B and B is related to C. A is related to B means A is less than equal to B and B is less than equal to C. Then we are saying what we will have, A is less than equal to C, because A, B, C, these are real numbers. So A is less than equal to C. So this means that this relation it is transitive relation. Why? Because this thing implies that A is related to C. Next is non-symmetry. We have to prove that this relation it is not symmetric. So to prove it is not symmetric, we have to give a counter example over here. So we are considering an A is equal to 4 and B is equal to 5. So this thing implies us that A is less than equal to B. It means we are talking about A is related to B. But now we have to check whether B is related to A or not. So to check this thing, we are saying that 5 is not less than equal to 4. So this thing implies us that 5 is not related to 4. This thing gives us 4 is related to 5, but 5 is not related to 4, because 4 is less than equal to 5, but 5 is not less than equal to 4. So we are saying that this relation is not a symmetric relation. Next we have is let S be the set of real numbers and R be a relation in S, and it is defined like the relation, it has a definition that A and B, they are related if A is less than equal to B square. We have to prove that this relation is neither reflexive nor symmetric nor transitive. So for first of all we are talking about the reflexivity. So if we consider any number A between say 0 and 1, if we consider any number A between 0 and 1, say we are considering A is equal to 1 by 2, then we will have A square is equal to 1 by 4, and clearly we have 1 by 2 is not less than equal to 1 by 4. So we are saying that this condition, the condition we have is that for all A is related to A, this does not hold here. This condition does not hold here. So we are saying that this relation, it is not a reflexive relation. We have found a counter example, that is if we take A is equal to 1 by 2, then 1 by 2 is not related to itself, that is 1 by 2 is not less than equal to B square. Next, second thing we have to prove is that it is not symmetric. So for symmetric we have to give, we have to prove that it is not symmetric. It means we have to give the counter example again. So suppose we are saying A is equal to 1 by 2 and B is equal to 1. Then what we have is that A is less than equal to B square. We are saying 1 by 2 is less than equal to 1. That is A 1 by 2 is related to 1. Now we have to check whether 1 is related to 1 by 2 or not. We are checking. We have to check whether 1 is related to 1 by 2 or not. So we are substituting the value over here. So we are writing 1 is less than equal to 1 by 2 square. This thing is not true. So this thing implies us that 1 is not related to 1 by 2. So what we get is that 1 by 2 is related to 1 plus, but 1 is not related to 1 by 2. So this thing gives us that this relation is not symmetric. Next we have to prove the transitivity. So we have considered the elements A is equal to 2, B is equal to minus 2 and C is equal to 1. Now if we look at these two elements A and B, we have is 2 is less than equal to minus 2 square. So A is related to B. If we look at these two elements over here, B and C, so we are saying minus 2 is less than equal to 1 square. It means B is related to C. Now if we look at the element A is equal to 2 and C is equal to 1, then 2 square is not less than equal to 1. It means A is not related to C. So what we get is for A related to B and B related to C, we have A is not related to C. It means this relation is not a transitive relation. Next is let N be the set of all natural numbers and R be a relation in N, and it is defined like A and B are related if A is a factor of B. We have to prove that R is reflexive, transitive, but not symmetric. So N is the set of natural numbers. So if we consider a natural number A belongs to N, we are writing it is A belongs to N means A is a natural number, then we know that A is a factor of A. It means A is related to itself by this relation, and this thing gives us that A is reflexive. Next is if A is a factor of B and B is a factor of C, it means B is equal to AM and C is equal to BN, for some m comma n belongs to n. Now we have to check whether A is related to C or not. So it means we are talking about, is there any number for which C is equal to K times A? We have to check this thing. Whether there is a number K such that C is equal to K times A. So we just substitute this value of B in this equation and we obtain that C is equal to A m into n. This is equal to A into mn. In place of mn, if we write K, so we get C is equal to K times A. So this thing gives us that A is a factor of C, and A is a factor of C means that A is related to C. So what we get is that for A related to B, B related to C, we have A is related to C. So it means this relation, it is a transitive relation. Next we have is that this relation is not symmetric. So we are going to give a counter example over here. So suppose we are considering that A is equal to 2 and B is equal to 6. Then clearly we have 2 is a factor of 6, but 6 is not a factor of 2. 2 is a factor of 6 means 2 is related to 6. 6 is not a factor of 2 means 6 is not related to 2. It means that this relation, it is not a symmetric relation. Next is let X be a non-empty set and let S be the collection of all subsets of X. We are saying now X is the any non-empty set and S is the collection of all subsets of X. That is, we are talking about S is the power set of the set X. R be the relation defined by R is equal to A and B are related if A is a subset of B. We have to prove that this relation is transitive but neither reflexive nor symmetric. So first of all, we have to prove that this relation is transitive. So we are considering any three sets A, B and C which belongs to this collection S. Collection S is basically the power set. It is collection of all subsets of X, and we have A is a subset of B and B is a subset of C. We are talking about A, B, C belongs to S such that A is related to B and B is related to C. So this thing implies us A is a subset of B and B is a subset of C, and this thing implies us that A is a subset of C. This thing implies us that A is a subset of C. It is important to note over here that we are talking about proper subset. So what we get is that for A related to B, B is related to C, this thing implies us that A is related to C. So this relation, it is a transitive relation. Next is we have to prove that this is non-reflexive. So we are considering any element A from this set S, and clearly we have A is not a subset of A. Again I am repeating, this is proper subset over here, and we are saying A is not a proper subset of A. In place of this, if we would have over here, it is A is a subset of B, subset equal to, then what we will have, A is a subset equal to B. This thing will be true, but A is a proper subset of A, this thing is false. So we are saying that this relation, it is not a reflexive relation. Next is if A is related to B, this thing implies us that A is a subset of B, proper subset of B, and if A is a proper subset of B, then B cannot be a proper subset of A. It means B is not related to A. It means this relation, it is not symmetric. Next, we have to give the examples of the relations. First is reflexive, a relation which is reflexive and transitive but not symmetric. So suppose we are saying that A is any set 1, 2, 3. Then we have defined a relation on this set R1 that is equal to, we are saying relation, it is basically the subset of the Cartesian product. So let R1 be the set, it contains the element 1, 1, 2, 2, 3, 3 and 1, 2. Then we are saying this relation is reflexive because for 1, 2 and 3, this 1, 1, 2, 2 and 3, 3, they are over there. So it means we are saying for all A belongs to A is related to A. It means this relation, it is reflexive. Next, we are saying that this relation is transitive. If we consider any two elements, any three elements A, B, C, such that A is related to B and B is related to C, then this thing implies us that A is related to C. We have to choose any three elements from this and we have to check manually whether they are satisfying this condition or not, and if you will check it, they are satisfying this condition. So as an example, I am showing you some calculations over here. Suppose I am taking A is equal to 1. We are saying 1 is related to, from here, 1 is related to either 1 or 1 is related to either 2. We are saying 1 is related to 1 or 1 is related to 2. Next, we are saying 2 is related to 2 or 2 is related to 1. 2 is related to 2, 2 is related to 1, and this thing implies that 1 is related to 2, and this thing implies us 1 is related to 1. This is, we have checked, if 1 is related to 1, 2 is related to 2, then 1 is related to 2. If 1 is related to 2, 2 is related to 1, then 1 is related to 1. Similarly, we have to check for every pair over here that this condition holds. Then we are saying that this relation, it is transitive. We are not saying that it holds for 2, then it will hold for all others. We have to check for all the values over all values. Check for all values. Next, we are saying that this relation is not a symmetric relation because we can see that 1 is related to 2 but 2 is not related to 1. That is, there is no element 2, 1 over here. So this is an example of a relation which is reflexive and transitive but not symmetric. Second is, we have to give the example of a relation which is symmetric and transitive but not reflexive. So this is the example. R2 is the relation given over here. Clearly the element 3, 3 is not there. This 3 is not related to 3. It means this relation, it is not a reflexive relation because 3, 3, it does not belong to R2. Next, we are saying it is symmetric because for 1, 1 belongs to R, 2, 2 belongs to R. If 1, 2 belongs to R, this thing implies 2, 1 belongs to R. And if 2, 1 belongs to R, this thing implies 1, 2 belongs to R. So this thing holds for all the elements A and B. So we are saying this relation, it is symmetric relation. Next, to check whether it is transitive or not, again we have to check all the cases that 1 is related to 1 and 1 is related to 2. This thing implies us 1 is related to 2. Next, for 1 is related to 1, we have this condition only. Next, we are talking about 2 is related to 1 is related to 2, and we have two conditions over here. 2 is related to 2 and 2 is related to 1. So this thing implies us 1 is related to 2 and this thing implies us 1 is related to 1. So both these elements, these are true. Similarly, we have to check for all other elements over here, and we can find that this relation is transitive relation. Next, we have to give the example of a relation which is reflexive and symmetric but not transitive. So on R we have defined this set. Clearly 1, 1, 2, 2 and 3, 3 they belong to this set. So it means this relation it is symmetric. Reflexive. When we are talking about symmetric, we are saying for 1, 2, 2, 1 element is there. For 2, 1, 1, 2 is there. For 2, 3 and 3, 2 are there. So it means this relation it is symmetric relation, that is A related to B implies B is related to A for all A, B belongs to A. Now we have to prove that this relation is not a transitive relation. We have to find an element over here. So to find that element, how we are going to start is, we look at this first element over here. It is 1 comma 1 is related to 1 and 1 is related to 2. This should imply that 1 is related to 2. This thing is true. Next we start with the element 2 is related to 1. We have the element 2 comma 2. This element we are talking about. 2 is related to 1 and we have 1 is related to 1 and 1 is related to 2. So this first thing implies us that 2 is related to 1 and this thing implies us that 2 is related to 2. These two are also true over here. Next we are talking about the element 2 comma 2. We are saying 2 comma 2 belongs to R. We are saying 2 is related to 2 and now we have again two conditions over here. 2 is related to 1 and 2 is related to 3. Now this thing should imply us that 2 is related to 1. This element is there, and this should imply us that 2 is related to 3. This element is also there. Similarly, if we keep on going like this, and if we look at this element, 3 is related to 2. Now 2 is related to 2, 2 is related to 1, 2 is related to 3. Look at this condition over here. 3 is related to 2, 2 is related to 1. This thing should imply that 3 should be related to 1. But this thing is not true. There is no element 3 comma 1 over here. So we are saying that this relation is not a transitive relation. Next is, we have to give the example of a relation which is symmetric but neither reflexive nor transitive. So this relation that is given to us over here, it has the element 1, 2 and corresponding to it, it has the element 2, 1. So clearly this relation, it is a symmetric relation, that is if A is related to B, then B is related to A. It is not reflexive because 1 is not related to 1, that is 1 comma 1 is not an element of R4. And it is not transitive because we are saying 1 is related to 2 and 2 is related to 1. This thing should imply that 1 is related to 1, but 1 is not related to 1. We are saying 1 is not related to 1. It means this relation, it is not a transitive relation. Next is the relation which is transitive but neither reflexive nor symmetric. So clearly the element 1 comma 1 is not there. So this relation, it is not reflexive relation. For 1 comma 2, 1 is related to 2 but 2 is not related to 1. For this element we are talking about, we have 1 is related to 2 but 2 is not related to 1. So this relation is not symmetric, but this relation is transitive. How we are going to check the transitivity? First element we are considering, it is 2 is related to 2. There is no element for which further we can go. Next we are saying 3 is related to 3. There is no further element we can go. Next we are saying 1 is related to 2 and 2 is related to 2, this thing implies us 1 is related to 2. So we are saying for A, B, C belongs to A, we have A is related to B, B is related to C, implies A is related to C. So it means this relation is a transitive relation, which is neither reflexive nor symmetric. Next is let n be the set of all natural numbers and let R be a relation on n cross n. And this relation is defined like A comma B is related to C comma D, implies AD is equal to BC. Now n is the set of natural number and R is the relation on n cross n. It is important to note over here, R is not a relation on n. We are saying n is natural numbers. To be a relation on R means R is a subset of, if it is given that R is a relation on n, it means R is a subset of n cross n. It is not this thing that is given to us. It is given that R is a relation on n cross n. It means R is a subset of n cross n cross n cross n. That is, the elements of n cross n, they will be in the form A comma B or C comma D. Now we have to prove that this is an equivalence relation. So first we are talking about the reflexivity. So we have considered an element A comma B that belongs to R. I am again repeating over here, the elements over here, they are in the form of ordered pairs. So clearly we have A, this thing is given to us. We are talking about this condition over here. We have to check whether A comma B is related to A comma B or not. Now what is the condition that is given to us? It is A comma B is related to C comma D if and only if A into D. A into D means we are talking about A into B, that is equal to B into A, and we know that this property holds for all natural numbers. So what we get is that A comma B is related to A comma B, that is this relation, it is a reflexive relation. Next we are saying this relation, we have to prove it is symmetric. So we are considering two elements from R, one is A comma B and second element we are considering it is C comma D, they belongs to R, such that A comma B is related to C comma D. What this thing means? This thing means that AD is equal to BC. What this thing means? That BC is equal to AD. And this thing implies us that C comma D is related to A comma B. That is, we have proved that if A comma B is related to C comma D, then C comma D is related to A comma B. It means this relation, it is a symmetric relation. Next thing we have to prove it is transitive. So we are considering three elements over here. The first element we are considering it is A comma B, next is C comma D, and next is E comma F. These are the three elements we have considered from the R, and we are considering that A comma B is related to C comma D, C comma D is related to E comma F. Now if A comma B is related to C comma D, it means we have AD is equal to BC, and if C comma D is related to E comma F, so we have CF is equal to DE. Now if we multiply both these equations, we will get AD CF is equal to BC DE. This A, B, C, F, B, C, D, E, these are natural numbers. It means none of them are 0. So this C gets cancelled and this D gets cancelled. So we are left with this AF is equal to BE. What AF is equal to BE means? That this thing implies us that A comma B is related to E comma F. We obtain that A comma B is related to E comma F if this condition A comma B is related to C comma D, C comma D is related to E comma F. This thing implies us that A comma B is related to E comma F. So we are saying that this relation, it is a transitive relation. If it is reflexive, symmetric and transitive, it means it is an equivalence relation. Next we have is, let R1 and R2 be two equivalence relation on a set A. We have to prove that R1 intersection R2 is an equivalence relation on A. Now suppose we are saying that R1 is a subset of A cross A and R2 is a subset of A cross A. Then first thing that we have is that R1 intersection R2, that will be a subset of A cross A, and this thing implies us that R1 intersection R2 is a relation on A. The first thing we have proved is that this is a relation on A. Now next we have to prove that if R1 and R2 they are equivalence relations, then this R1 intersection R2 is also an equivalence relation. Now if R1 is an equivalence relation, then we have for all A belongs to R1, or we are saying for all A belongs to A, this thing implies us that A comma A belongs to R1. R2 is also an equivalence relation, it means it is also reflexive. It means A comma A belongs to R2. We are saying for all A belongs to A comma A belongs to R1, A comma A belongs to R2, because both of these are the reflexive. So combining this result, this thing implies us that A comma A, it belongs to R1 intersection R2, and this thing gives us that this relation is a reflexive relation, that is R1 intersection R2. For all A belongs to A belongs to R1 intersection R2. R1 intersection R2 itself, it is a relation. So we are saying that R1 intersection R2 is reflexive. Now the next we have to prove is that this relation is symmetric. So to prove it is symmetric, suppose we are saying that A comma B, it belongs to R1 intersection R2. Then this thing implies us that A comma B belongs to R1 and A comma B belongs to R2. Now what is given to us is that R1, R2, these are the equivalence relation. It means they are symmetric. If these two relations are symmetric, it means what this thing gives us, A comma B belongs to R1 means B comma A belongs to R1. And this second condition, A comma B belongs to R2 means B comma A belongs to R2. Combining these two results, we get that B comma A, it belongs to R1 intersection R2. So what we get is that for A, B belongs to the set A comma A and B, these are related by the relation A1 intersection A2. Then this thing implies us that B comma A, these are related by the relation R1 intersection R2. So this thing gives us that this relation, it is a symmetric relation. Next we are talking about it is the transitivity. So we are saying suppose A comma B, it belongs to R1 intersection R2. B comma C, this belongs to R1 intersection R2. Then what we have is A comma B belongs to R1 and A comma B belongs to R2. Further, B comma C belongs to R1 and B comma C belongs to R2. I am again writing these conditions over here. We are saying that A comma B, it belongs to R1 intersection R2. B comma C, this belongs to R1 intersection R2. This thing is thus A comma B belongs to R1 and A comma B belongs to R2. This gives us B comma C belongs to R1. This gives us B comma C belongs to R2. And it is and in between these two conditions. It is and over here. It is and over here. Now, look at these two conditions over here. This first A comma B belongs to R1 and B comma C belongs to R1. We are talking about these two conditions. A comma B belongs to R1 and B comma C belongs to R1. These two conditions we have written separately. And A comma B belongs to R2 and B comma C belongs to R2. These two conditions we have written separately. Now, the given relations R1 and R2, they are transitive. It means if A comma B belongs to R1 and B comma C belongs to R1, this thing implies us A comma C belongs to R1 and A comma C belongs to R2. This thing implies us that A comma C belongs to R1 intersection R2. So what we get is that for A comma B belongs to R1 intersection R2, B comma C belongs to R1 intersection R2, we have A comma C belongs to R1 intersection R2. So it means that this relation R1 intersection R2 is a transitive relation. Now the next thing we have is we have to give an example to show that the union of two equivalence relations need not be an equivalence relation. In the previous question we have proved that the intersection of the equivalence relations are equivalence relations. Now we are proving that unions need not be equivalence relations. So we have considered a set A over here. We have considered two relations. One is the relation R1 is equal to this and second is the relation R2 is equal to this. First of all, we have to prove that both these relations R1 and R2, these are the equivalence relations. This thing is easy to prove. We are saying all 1 1 2 2 and 3 3, 1 1 2 2 and 3 3 are there. If 1 is related to 2, then 2 is related to 1. If 1 is related to 3, then 3 is related to 1. Similarly, we can check the transitivity in all these cases. If suppose I am talking about this case, we are saying 1 is related to 1 or 1 is related to 2 and 2 is related to 1 and 2 is related to 2. So these two will imply that 1 is related to 1, these two will imply that 1 is related to 2 and both of these elements are there. Similarly, we can check for all other pairs and we obtain that both these relations, these are the equivalence relations. Now if we write the intersection of these two, we have union of these two, we have R1 union R2, that will be 1 comma 1, 2 comma 2, 3 comma 3, then 1 comma 2, then 2 comma 1, 1 comma 3 and 3 comma 1. Now clearly this 1 1 2 2 and 3 3 are there. For this 1 comma 2 2 comma 1 is there. For this 1 comma 3 3 comma 1 is there. It means both this relation R1 union R2, it is symmetric as well as reflexive. But if we look at the element, I am talking about 3 is related to 1. I am talking about this element over here. Corresponding to this, we have 1 is related to 1 and another element is 1 is related to 2 and 1 is related to 3. After this, you are seeing 3 is related to 1. After this, we have these three cases, this, this and this. Now look at these two values over here. 3 is related to 1, 1 is related to 2. Then we should have, we are saying A is related to B and B is related to C. Then we should have A is related to C, but this thing does not imply that 3 is related to 2. because there is no element 3 comma 2 over here in this list. So we are saying that 3 is related to 1, 1 is related to 2, but 3 is not related to 2. So this relation, it is not a transitive relation. So this relation is not an equivalence relation. So this is a counter example to show that the union of two equivalence relations need not be an equivalence relation. But the intersection, we have already proved that intersection of two equivalence relation is always an equivalence relation. Next we have is the definition of equivalence class. So we are suppose a set A is given, we have a set A, and there is an equivalence relation R defined on that set A. We have considered an element A belongs to A. We are talking about, we have considered the element A. For any element we are saying, we are talking about the set or the collection of all those elements of A such that A and B, these two are related. Then this set, this is called the equivalence class of the set of equivalence class corresponding to this relation on the set A, and this class, it is denoted like this. The first property we have is that two equivalence classes are either disjoint or identical. It means if I am talking about any set, I am saying there are two elements, say A and B, I am considering from A, or say I am talking about the elements A1 and A2. I am writing the equivalence class of A1, I am writing the equivalence class of A2. It is all those elements B1 belonging to A such that, or in place of B1 we can write it is all those elements B belonging to A such that A1 comma B, these are related to each other. Second we are talking about, it is collection of all those elements of A such that A2 comma B, these are related to each other. Then we are saying either both these classes, they are identical, means they are equal to each other, or they don't have any element common between them. And an equivalence relation on a set A, it makes the partition of the given set. We are talking about, suppose this is the set A given to us. We have chosen any element over here, say A1. Next we have chosen the element, say A2. Next we have chosen the element, say A3. Corresponding to A1 we have obtained the collection of all those elements of A which are related to A1. Then we have chosen A2 and we have obtained all the elements of A which are related to A2. And then we have chosen this A3 and all the elements which are related to of A which are related to A3. So we are saying these are the elements which are related to A3, these are the elements which are related to A2, and these are the elements which are related to A1. So we are saying that we have partitioned this set A into mutually disjoint equivalence classes. That is A1 equivalence class of A1, union equivalence class of A2, union equivalence class of A3, that is equal to A, and A1, A2, A3, these are mutually disjoint. Mutually disjoint means that A1 intersection equivalence class of A2, that is equal to phi. A2 intersection with equivalence class of A3, that is equal to phi. Similarly for the third case. So based upon this definition, we have this problem. It is R is equal to A and B. These are the integers, and A and B, they are related to each other if A minus B is divisible by 3. We have to prove that R is an equivalence relation, and we have to find the partition of the set of integers. So to prove that it is an equivalence relation, we are saying A minus A is equal to 0, which is divisible by 3. So this thing implies us that A is related to A. Second, we have to prove the symmetry part. So we are saying if a minus b is divisible by 3, this thing implies us that b minus a is divisible by 3. You can consider the integer m over here, and correspondingly you can prove this result. So we are saying that this thing implies us a is related to b implies a minus b is divisible by 3. B minus a is divisible by 3 implies us b is related to a. So combining these results, we are saying that this relation, it is symmetric. Next we are saying let a, b and c, these are the integers, such that a is related to b and b is related to c. So this thing implies us that a minus b is divisible by 3. It means there is some integer m such that a minus b is equal to 3 times m. M is some integer. Similarly, b is related to c means b minus c is divisible by 3. So this thing implies us b minus c is equal to 3n, where n is some integers. Now if we add these two equations, we get a minus b plus b minus c. This will be equal to 3 times m plus n. These two gets cancelled, so we are left with this a minus c is equal to 3 times m plus n. So this gives us a minus c is divisible by 3. A minus c is divisible by 3. So we have proved that this relation, it is reflexive, symmetric and transitive. So it is an equivalence relation. Next we have to find the partition of the set of integers using this relation. So we start writing the equivalence classes corresponding to the elements. So first element we are considering, it is the 0. It belongs to z. So we are writing the equivalence class of 0. So we are writing equivalence class of 0 means all those integers z such that 0 and x, these are related to each other. 0 and x are related means we are talking about that x minus 0 or 0 minus x, this should be divisible by 3. So what is the collection of all these elements? We are saying it is 0, 3, 6, 9, so on, minus 3, minus 6 and so on. So this is the collection we are talking about. So the equivalence class for 0 we have, it is this. Next we are considering the element 1. Equivalence class of this side will be all those x belongs to z such that 1 minus x is divisible by 3. So the answers we will have, it is 1, 4, 7, 10, so on. Then it is minus 2, minus 5 and so on. The next number we have, it is 2. So it is x belongs to z such that 2 minus x is divisible by 3. So the collection we will have, it is minus 4, minus 1, 2, 5, 8 and so on. Now suppose we are writing the next element, say it is 3. So equivalence class of 3 means we are talking about all those x z such that 3 minus x is divisible by 3, and this collection will be equal to 0. So what we are getting is that this 0, that is equal to equivalence class of 3, that is equal to equivalence class of 6, that is equal to equivalence class of 9 and so on. Equivalence class of 1, that will be equal to equivalence class of 4, that will be equal to equivalence class of 7 and so on. Equivalence class of 2, that will be equal to equivalence class of 5, equivalence class of 8 and so on. Next we have is this equivalence class of 0, its intersection with equivalence class of 2. Its intersection with equivalence class of 2, it is 5. So we are saying these three equivalence classes 0, 1 and 2, these are mutually disjoint. So we are writing over here that z is equal to equivalence class of 0 plus union equivalence class of 1 union equivalence class of 2, and this is called the partition of z into the mutually disjoint equivalence classes. Next is let A is equal to, this set is given to us, x belongs to z, it is an integer such that 0 is less than equal to x is less than equal to 12. These are numbers 0, 1, 2 up to 12. And R is the relation, it is A comma B such that mod of A minus B is a multiple of 4. Then we have to prove that this relation R, it is an equivalence relation. And first of all, we are listing the elements of this set A. So these elements, these are A is equal to 1, 2, 3, 4 up to 0, 1, 2, 3, 4 up to 12. So if we look at this relation R, we consider any element A belongs to this set A, then mod of A minus A, that is equal to 0, and it is a multiple of 4. So this thing implies us that A is related to A, and hence this relation is a reflexive relation. Next, second step we have is, if we consider two elements A comma B belongs to A such that A is related to B, it means mod of A minus B is a multiple of 4. This thing implies us mod of B minus A is a multiple of 4, and this thing implies us B is related to A. So we get that this relation, it is a symmetric relation. Next step we have is, suppose there are elements A, B, C from A such that A minus B mod, this is a multiple of 4. Multiple of 4 means there is some number M such that, M means we are talking about M is some integer, such that mod of A minus B is equal to 4 times M. Mod of B minus C is equal to 4 times N. That is, we are saying A is related to B, this thing B is related to C. Now if we look at this value, mod of A minus C, that will be equal to mod of A minus B into B minus B minus C mod. And what we have done, we have added and subtracted B to this equation, and this thing will be equal to mod of 4m minus 4n. 4 comes out, it is mod of m minus n. It means A minus C is a factor of, is a multiple of 4. It means A is related to C. So what we have obtained, A is related to B, B is related to C. This thing implies us A is related to C. It means this relation is also a transitive relation. Now next we have to calculate all the elements which are related to 1. So elements related to 1 means equivalence class of 1. So we are writing it is all those x in A such that x is related to 1. It means all those elements in the set A such that mod of x minus 1 is a multiple of 4, and this set comes out to be the elements 1, 5 and 9. These are the elements, these are the values of x for which mod of x minus 1 is a multiple of 4. So this is the equivalence class corresponding to the set, the element 1. Now next we have is this set A is given to us. It has elements from 1 to 9, and R is a relation defined on A cross A. It is important to note over here, the R is a relation on A cross A means the elements of R, they will be of the form ordered pair, and the relation R is defined in this form, that it is A comma B is related to C comma D. This thing implies and implied by A plus D is equal to B plus C. We have to prove that this is an equivalence relation. So if we consider any element A comma B which belongs to R, then we have A plus B is equal to B plus A, and this implies us that A comma B is related to A comma B, and hence it is a reflexive relation. Next we are considering two elements One is A comma B and second is C comma D. Both these elements, they belong to R, such that A comma B is related to C comma D. Then this thing implies us that A plus D, that is equal to B plus C. This thing implies us B plus C is equal to A plus D. And this implies us that C comma D is related to A comma B. So what we get is that A comma B is related to C comma D. This implies us that C comma D is related to A comma B. So what we get is that this relation is a symmetric relation. The last part we have is, we have to prove that this relation, it is transitive. So we have considered three elements, A comma B, C comma D and E comma F. These are the three elements which we have taken from the set R, such that A comma B is related to C comma D. C comma D is related to E comma F. Now from the first one, we will obtain that A plus D is equal to B plus C. And from the second, we will obtain that C plus F is equal to D plus E. Now if we add both these equations, we will obtain A plus D plus C plus F, that is equal to B plus C plus D plus E. This C gets cancelled, this B gets cancelled, and we are left with this A plus F is equal to D plus E. And this thing implies us that A comma D, it is not B that is cancelled, it is D that is cancelled. So we are left over here, it is B plus E. So we get A comma B, it is related to E comma F. So what we have is that for A comma B related to C comma D and C comma D related to E comma F, we have A comma B is related to E comma F. It means this relation is also a transitive relation. So from all these three conditions, we obtain that this relation is an equivalence relation. Now next we have to calculate is the equivalence class corresponding to the element 2 comma 5. So equivalence class corresponding to 2 comma 5 means we are saying we have to find all those elements A comma B belonging to n cross n, such that 2 comma 5 is related to A comma B. What this thing means? That 2 comma 5 is related to A comma B means that 2 plus B is equal to 5 plus A. And this thing implies us that B minus A is equal to 3. And if we list all these elements, this is the collection we obtain. We are saying out of these numbers A, we have to find all those numbers B and A such that B minus A is equal to 3. So if we put A is equal to 1, we are saying what is the number for which B minus A is 3? It is the number 4 we have. So the first element we obtained is 1 comma 4. Next, if we put A is equal to 2, the corresponding number we will have it is B is equal to 5. So the next number we have it is 2 comma 5. So if we list all these numbers, we will get the list in this form, that these are the numbers which are related to the number 2 comma 5 by this relation. So this is the equivalence class determined by this element 2 comma